Well, welcome here. Your Sioux Falls physics teachers are here. We're going to do some free body diagrams with you here today. So we got 5 different scenarios here. And what we want to think about is a free body diagram is a diagram where we are going to draw all of the forces that are acting on the object. So let's look at situation A here. All right, it says a textbook sits motionless on a table. Okay? So here's my textbook, which is right now floating in the air, but we'll draw a little table that it is resting on. Okay? And if it's sitting motionless on the table, motionless is a big key here. So since this is not accelerating, we know that the net force acting on this book is going to be 0. There's going to be essentially 2 forces. We know that we have the weight of the book downward. All right, that is caused by gravity. And we also know that there must be an equal but opposite force that is counteracting that since the book is motionless. So we would draw in a normal force from the table that is directed upward. And in this situation, those 2 forces would be equal to each other.
Okay, now notice that this one, of course, was simple because everything canceled out. In our next situation, we have a baseball falling downwards without air resistance. And so, again, we have the weight in the downwards direction. And we also then would not have any air resistance. Now, in some cases, we might have air resistance in the upwards direction, but this has specifically told us that that air resistance is negligible. So, in reality, we actually have all of the forces summarized just with the weight. And if we think about what we're looking at with the baseball, it makes sense. If there's no force in the upwards direction to cancel out that weight, then we end up having a net force in the downwards direction, which is, of course, why the baseball accelerates.
Okay, here's our next situation. We have a truck now that is moving to the right at a constant velocity, and we are including air resistance this time. So if the truck is moving to the right, we would assume that there is what we would call an applied force by the truck. That's the truck's engine turning the wheels of the truck to the right in that direction. But there is air resistance, and air resistance would be working opposite of that applied force to slow the truck down. So we would also then include a force this direction. I might call it force of air. That is air resistance that would be opposite of the applied force. Now, key phrase here, constant velocity. All right? That means there is no acceleration. Without acceleration, then, we know that the net force that's acting on this truck must be 0 newtons. Okay? That is a 0. That's not the word on. Okay? 0 newtons, folks. Net force must be 0 newtons if I have a constant velocity. So what does that mean? Well, that simply means that our applied force is equal to the force that the air resistance is applying. Now, in actuality, there would probably also be another force that we might need to consider a little bit here, and that would be from the road itself that the truck is driving on. There's probably some friction, but that amount of that friction would be much smaller, pretty negligible compared to the air resistance that a truck would undergo. Okay, to finish this out, there would also be vertical forces. We know that the truck has some weight down, okay, that it's sitting on the road with, and then the road must also be providing that normal force upward, okay? And again, those forces would be canceling each other out because the truck is not accelerating vertically at all.
Our next situation is a rocket accelerating upwards as it is launched. It does say include air resistance, so it must be a pretty significantly large force in this case. We'll start again with an arrow downwards for weight. And notice that in this case then, if the rocket is traveling with a velocity in the upwards direction, air resistance always acts against movement. So that means that our air resistance then would be in the downwards direction also. So we have the weight pulling down. We also have the air resistance working against its motion in the downwards direction. And now we turn to the upwards direction. The rocket is going to have some sort of a propellant, okay, some sort of an applied force, we could say, in the upwards direction. But notice that in this case, it is again key that as it travels upwards, it is accelerating. So whatever arrow we put in the upwards direction to show that applied force needs to be larger in size than the weight and the air resistance together. So our applied force in the upwards direction should give us more upwards force than we have downwards forces, and that would give us a total net force in the upwards direction, causing it to accelerate.
Okay, and for our last example then, we're going to look at this situation. We have a car traveling to the right, and it slows down using its brakes. Okay, so again, cars on the road here. Again, we would certainly have the weight of the car down on the road, and the road itself providing a normal force upward, and those would be equal to each other. We know if the car is slowing down, then it is undergoing a negative acceleration. So even though the car is traveling now to the right, okay, this is the direction of its motion, okay, this is the velocity it is undergoing, or the motion that is undergoing, the car is slowing down. So what kind of forces would be causing that to happen? Well, it says it applies the brakes. So the brakes are working against that motion, so we would expect to see a force directed this way from the brakes. Okay? And you could think of that as a force of friction, if you will. So if, in this case, then if they are applying the brake to the car, we would assume then that they're also not pushing the gas pedal anymore, so there would actually be no force directed to the right. Even though the car's motion again is in this direction, okay, there is no applied force that is causing that to happen at this instant. Obviously at one point there was, because the car was moving that way, but now at this point when it's slowing down, there is no force being applied to the right. The force direction that is slowing down the car would be the brakes that is directed left. So this is a good example here of a net force then that is directed in the opposite direction of motion. And this is when this happens is when we see a situation where we have something de-accelerating or slowing down. Alright, this is a problem for you here on Newton's second law. It says that we have a worker pushing a 12 kilogram crate with an applied force of 48 newtons. The crate also experiences a force of friction of 42 newtons. So first thing we're going to do here, and this is a good idea on any of these types of problems, is to first start by drawing a free body diagram. So let's just draw a little sketch here of what we have. So here's a little crate that I drew in there magically, and we're going to say that it's on the ground. So it says that the worker is pushing this with an applied force of 48 newtons. Now it doesn't tell us what direction, but I'm just going to arbitrarily say, okay, it's being pushed to the right. So we have an applied force here of 48 newtons. It also says that the crate experiences a force of friction of 42 newtons. We know that that force of friction would oppose the motion, so it is going to be directed in the opposite direction at 42 newtons. All right. Now, what other forces also exist on this crate? even though this doesn't necessarily come directly into this problem right now, we should go ahead and draw this in. The crate definitely has a weight that would be directed downward. We actually know the value of that since it's a 12 kilogram crate. That weight would be approximately 120 newtons. And there's also a normal force directed upwards that the ground is providing on that crate. It also would be 120 newtons because there's no movement or no acceleration of the crate in a vertical direction. So that essentially talks about part A then of the free body diagram. So let's move on then to part B. It says to calculate the acceleration of the crate. So we're going to go right back to the familiar equation of F equals ma. And the force here that is going to determine this acceleration is the net force that's acting on the crate. So to find that net force, we simply have to look at the forces that are acting in the direction of motion, which is horizontal in this case. And we know that we have a 48 Newton applied force and a 42 Newton frictional force that is opposing that. So my net force here is 6 newtons. So plugging that in, if I have a 6 Newton net force, the mass of the crate is 12 kilograms. And now I can simply solve that for the acceleration. And I get an acceleration of 0.5 meters per second squared.
Okay, let's continue on then with part C of this problem. Calculate the applied force necessary for the crate to accelerate at 0.65 meters per second squared. Now in part B, we just found that its current acceleration is 0.5 meters per second squared. This time we want a greater acceleration. So that tells us then that this applied force of 48 newtons is going to need to increase. The first thing we want to find is we want to find the net force required for this acceleration. So we'll be using the exact same equation that we just did. This time, again, a mass of 12 kilograms. This time plugging in the given acceleration of 0.65 and calculating that out, we get a net force of 7.8 newtons. Now again, that represents the net. So what that needs to tell us then is how much greater this applied force is than the friction force that is opposing it. Well, our friction force is already 42 newtons. So if we need an additional 7.8 newtons, that's the extra force that will cause the acceleration, we find that our new applied force is going to be equal to 49.8 newtons. With that amount of applied force, then the net force will be sufficient to give us an acceleration of 0.65 meters per second squared. Well, hello everyone, and welcome to another problem on Newton's laws. This one's going to look specifically at the example of mass and weight. First of all, we have an astronaut with a mass of 70 kilograms on the surface of the Earth, and it has 3 things for us to determine. First of all, part A is to determine the astronaut's mass on the moon. Well, notice that the mass is given as 70 kilograms on the surface of the Earth, and in a way, I guess you could think of this as a little bit of a trick question because mass does not change. When you travel to different locations, that mass value is still the same. Assuming you haven't gone on a diet or gotten a few extra pounds there, 70 kilograms would still be the mass regardless of the astronaut's location. That leads us to part B, which is to determine the astronaut's weight. Now remember, when we talk about weight, that weight is a force. It is the force of gravity pulling down on you at a given location. That means it is measured in newtons, and it changes depending on the amount of gravity at a given location. Now, a couple of different ways we can write this. One is to just use our Newton's second law. Net force equals mass times acceleration. Sometimes when we are talking specifically about gravity, that is rewritten by saying weight, or the force of gravity, is equal to mass times g, or the acceleration of gravity. And so now we can see then that depending on location, this acceleration value will change. Okay, for Earth, that's 9.8 meters per second squared, or approximately 10. So if we're going to calculate the astronaut's weight on the surface of the Earth, then all we need to do is include our 70 kilograms as his mass, and 10 meters per second squared as the acceleration of gravity, and we get the net force, or the weight, as 700 newtons. So when he stands on the surface of the Earth, gravity pulls down on him with a force of 700 newtons. Now that makes part C very simple because we're doing exactly the same calculation. Okay, again, our net force is equal to the object's mass times acceleration. His mass is still 70 kilograms, even though he's now on the surface of the moon. The only thing that has changed is that on the moon, we have a smaller acceleration of gravity. And so it gives in the problem that that is just 1.6 meters per second squared. Compare that, by the way, to 9.8, and you can see why things would feel much less weight on the moon. If we multiply those out, we get 112 newtons as the astronaut's weight on the moon. So while on Earth, gravity pulls down on him with 700 newtons, but on the moon, gravity there would only pull with 112 newtons.
Hey, your Sioux Falls physics teachers are back here. We got another helping of Newton's second law, so just, belly on up to the table here. This will be some good stuff. We've got an old 270 kilogram car going down the highway. It's going 21.5 meters per second and experiences a resistive force of 620 newtons. That could be air resistance, or maybe it hits a deer, who knows, okay? Driver presses the accelerator for 2 seconds and causes the velocity to increase to 23.5 meters per second. We're going to determine the applied force created by the car's engine as the car accelerates. All right, so let's first of all just kind of start off here by looking at the situation and thinking about the forces that are involved in the problem. So a little free body diagram here. So here's my car driving down the road. We know that the car is moving at a certain velocity. It's not accelerating to start with, okay? But so the resistive force that is on the car itself here is 620 newtons, okay? So if we want to think about the force resistive equaling 620 newtons, if the car is not accelerating, then we know that the car itself is applying a force that is equal to that. Now, it does tell us that the driver presses the accelerator for 2 seconds and accelerates the car to a new velocity of 23.5 meters per second. So one of the first things that we have to do then in this problem is to figure out, okay, how much acceleration did the car actually undergo? Well, the change in velocity is the difference in speed. So we ended at 23.5, we started at 21.5, so we underwent a change in velocity of 2 meters per second. Okay? The acceleration is equal to that change in velocity divided by the time that it took to do that. Well, it took 2 seconds. So if I have a change in velocity of 2 meters per second, it took 2 seconds to do that. That now makes my acceleration 1 meter per second squared. Okay, now remember, we are trying to figure out what the applied force of the car's engine is when the car is accelerating. Okay, so now that I know my acceleration, all right, I can figure out what the net force is that is acting on the car. Because we know that the net force that's acting on the car while it accelerates has to be equal to its mass times its acceleration. So, F net is going to be equal to the mass of the car, which was 270 kilograms, multiplied by that acceleration of 1 meter per second squared, giving us a net force then on the car of 270 newtons. Now keep in mind that's the net force that's acting on the car. That is not answering the question, which is what is the applied force created by the car's engine. Remember, we said initially that when the car was not accelerating that the resistive force of 620 and the applied force of the car were the same. But now that the car is accelerating, we know that there must be a positive net force. In fact, we know that that net force is 270, so that means the applied force can no longer be 620 newtons. Instead, my applied force needs to be equal to the resistive force plus the 270 newtons. Okay? Another way of thinking about this is this way, is that I know that F net, okay, is equal to my applied force minus my resistive force. And if I know the net force is 270 newtons, and I know my resistive force is 620 newtons, then if I take 620 plus 270, that would give me my applied force, which in this case is equal to 890 newtons.